Hello and good afternoon or morning or evening, depending on when you're joining us here at the Innovate to Build conference. And thank you for joining my talk. I'll just get started. You're tuning into Future Details with me, Ashley Kacha. I'll just speak to you about myself just very shortly and what this talk is about, because it's a little bit more esoteric than perhaps some of the other talks here at the conference. So, just a little bit about me. My name's Ashley. I'm a structural engineer by training and trade, by profession. Currently, I'm the Senior Engineer for Digital Workflows and Computational Design at the Institution of Structural Engineers here in the UK. Of course, many of you are familiar with our work. And I will say that photo was taken quite some time ago, so apologies if I look a little bit different. My responsibility in the institution is to coordinate much of the digital engineering aspects of the institution's work, and that ranges from sort of near-term aspects of digitization, such as analysis, computational design, a lot of BIM work, for example, all the way up to sort of more of the sort of future gazing and horizon scanning is what I suppose it's called, in terms of the future adoption of technology in the construction sector, and specifically to do with structural engineering. So, what is this all about? Well, again, as I mentioned, really it's about speculative engineering, future gazing. From my perspective, my work is all about dreaming of things that don't quite exist yet, or are in the early stages of being developed, and to speculate on how those things will interact with engineering and construction, specifically structural engineering in the future, both in the near-term future and the long-term future. The talk was really off the back of a short blog article I wrote for the institution this time last year. It's called Concepts, Computation and Innovation, inspired by art and structural engineering, where I explore some of the aspects of how science fiction and fiction more generally has, and artwork specifically, has inspired my view of how construction professionals and engineers can really help achieve a vision of the future. And I'll just go through a few of those inspirations just very quickly right now. So if you are interested in having a look at that blog, please do take a look at the Institution of Structural Engineers website. It's on there, freely available, of course. So yeah, I've heard some good things from people, so hopefully it'll be inspirational to you as well. This really begins with my fascination with artwork more than anything else. Some of the sci-fi novels I read as a child, and some of the artwork I saw, and the movies and the cartoons, in this case anime, for example, and manga, has really inspired me to look into what the sort of built environment could be like. And here we see sort of two things, quite different. Floating City by Chris Foss, who did a lot of work on sci-fi novels in the 80s and in the 70s and 80s rather, and Appleseed, one of my favorite anime. And the idea is to really sort of look at inspiration for the future, to be outcome driven for the future, to have a vision for the future, and to think holistically for the future. A few other inspirations I draw on are concept architecture, for example, Vincent Galabon architectures for Paris Smart City 2050. This is Rapture from a game called BioShock, which is a little bit old now, but it's an underwater city, for example. It's in sort of very Art Nouveau, Art Deco sort of era. And of course, there are some slightly less optimistic looking structures and sort of visions of the future we could have. This is sort of Megacity one from the movie Dread in 2012, I believe. It's a dystopian sort of cityscape of concrete towers, taller than the tallest buildings on the planet currently. Housing hundreds of thousands of people. And, hive cities housing billions in the Warhammer 40,000 fantasy setting. So I'm going to go through a few of the future inspired structures and sort of structural paradigms that sort of exist out there, and we'll look at some of the sort of detailing aspects a little later on, and sort of how some of this comes together really. So first we're going to start with the megastructures. From my point of view, megastructure is probably the easiest thing to understand. Here are some concepts for example, this one was Ultima Tower. Designed to be placed in the one on the sort of the right-hand side is Ultima Tower, designed to be placed in the middle of San Francisco, I think, San Francisco Bay. You can see the scale of these things. It's looking at I think it says there 5,400 feet, which is about 1,000 meters. Is that right? No, maybe about 1,500 to 2,000 meters. So it's 2 kilometer high tower. It's astonishing. So, it does say there. Sorry, 3,353 meters. And another concept actually, which is slightly more recent, for example, is sort of a ring encircling the Burj Khalifa. I don't know who the architect is, I'm afraid, but these sorts of things are sort of quite inspirational to me. This was one of the sort of quite early examples of a megastructure. The city in Tokyo Bay, which was scheme designed, I believe, and never really came to full detail fruition. And you can sort of see the scale of those, the sort of circular nodes, the personal rapid transit nodes, and the skyscrapers effectively hung in between. The idea was to be seismically resistant. So you can see sort of the type of structures that we're sort of hoping to sort of have a look at the detailing of, in this talk. Another paradigm is adaptive structures. A little bit more nuanced, a little bit more esoteric, I suppose. And that's a structure that changes itself based on the internal or external environment, responding to loads, use cases, and such. So this could be a tower that changes shape, for example, like in this case here. They could be adaptive facades, systems that automatically sort of respond to, say, humidity or heat, those sorts of things. And to a large extent, they're modeled on biological systems in the sense that biological systems are often adaptive. We as human beings, for example, can move from side to side and still remain stable. We can be pushed and moved, and we are sort of stable in ourselves. We're a dynamic system that moves around. So there are sort of benefits to that sort of thing. And those benefits include, of course, efficiency, resilience. These sorts of adaptive structures offer advantages over traditional static structures, again, including enhanced efficiency, resilience, safety, and sustainability by dynamically adjusting as external factors like environmental conditions, user requirements, loads, they all change and morph the type of structure, the structure itself. They can optimize their performance in real time, reduce resource utilization, of course, that's the efficiency side of things, and they can respond to changing needs and evolving design constraints, more flexible in their design. Much like the human body is very flexible in what it's able to do. Well, in an ideal world, they would also help, enhance comfort and safety, and be able to respond long term to effectively external stimuli. Some examples, quick examples of some adaptive structures. This is a Falkirk wheel. It's not quite an adaptive structure, it's more of a mechanical structure, I suppose. It's designed to take boats from a lower level to a high level. This is in Scotland. It's quite a few years old now. It's over 15 years old, I believe. But this is an example of a counterbalance. So it uses very little energy because the water weight on top and the water weight on the bottom is always the same due to sort of displacement laws, water displacement laws, but weight and volume. Here's another one. This is the Rolling Bridge by Heatherwick Studio. This was 2002, I believe, and it's a bridge that unfolds to allow boat traffic to move across. And a more recent example is one by Cake Industries. This rolling bridge is a perfect example of an adaptive structure, a structure that can move and respond to its requirements, sometimes letting boats through, other times being a footbridge so that people can move across, and very efficient. This particular version is hand cranked because it's perfectly counterbalanced, and these are sorts of the examples of things, structures that change according to requirement or environmental conditions, for example, where they need to change shape effectively. The sort of next paradigm is sort of self-assembly. These are structures that morph to either assemble themselves into a certain configuration. This is sort of like almost an evolution of an adaptive structure, but more on a component level. So here we see a sort of almost a bending active structure, which is counterweighted. Here we see a self-assembling programmable table, they call it, and of course, sort of from a more sort of robotic standpoint, we've got structures that could be reassembled in a modular sort of fashion, effectively build themselves, which can apply in sort of orbital environments. And that's sort of the crux of a few sort of different structural paradigms in sort of future detailing, I suppose. And the real interesting part for me is how the structural engineer's role changes over time based on these new sort of structural paradigms or requirements that could potentially sort of impact the construction industry more generally. And so I like to have a look at some of the more detailed aspects rather than these sorts of overall scheme designs, sort of really understand how we as designers really sort of should respond to these sorts of things. So we've got a sort of quick list here of sort of aspects that could generally impact the role of the structural engineer. So from sort of top down, we've got the actuation mechanisms, sort of sensor integration, control system design for maintenance, ensuring durability. There's a safe failure condition as well, of course, which is quite important for the things that move and may house many people. So, and then we've got the computational core, which is sort of ties it all back together with the things that we're doing now and sort of how we can sort of navigate our way towards the future. And through these categories, a few of these categories anyway, we're going to look at just a quick detailing example, which might be applicable to some people. Someone in the future perhaps. And this is one which is a fairly simple idea. It's a sort of multi-stable core. The idea being that this core, for example, is a very crude design example. It's a multi-story structure. The levels of the core are hinged, providing sort of some nominal lateral stability to the structure. However, it's almost like the human spine, for example, where it flexes. Each floor or group of floors are attached effectively as outriggers to the central core, and there is an actuation system of some description that runs through the structure. Perhaps they could be cables or like a rack and pinion mechanism, or like hydraulic rams or something similar. And this is an example of sort of more of the sort of adaptive type structure, but equally applicable to sort of mega structure type buildings that we looked at before. The way that I envision this to work is during a severe winds or a high gust or something, the hinged aspect would allow the core to flex in a certain direction. And after that, of course, it being sensed or sort of controlled by the main control system, actuators would engage and pull the core back into position in order to sort of resist some of those wind loads. And that could reduce, for example, the interstory drift. For those of you who are structural engineers, you'll understand that sort of the drift limitations between stories as you get higher and higher become increasingly onerous, especially due to wind loads. As you get higher, you get huge amounts of deflection, lateral deflection, and sort of effectively large cantilevers. And so, a controlled actuation system could potentially pull that building back into position. Well, what would that sort of actuation system look like? Well, there are lots of sort of mechanical ways of actuating things, and you can begin to see here where the detailing aspect comes in. Actuation mechanisms such as these hydraulic rams, for example, may pull or push. You can have a couple which pushes one side and pulls another, and forces the building back into position. Perhaps a ratcheting system which pulls slowly in one direction or the other. And the connection points between these and the main structures are, of course, some things that need to be designed, and things that would be structural engineers in the far future potentially would need to account for. There is also, of course, sort of a potential tension cable aspect to it. So large cables could be tensioned in order to actually connect to each core, and tensioned in order to deal with the deflection. And so what would that look like? Well, let's look at a quick detail here. So, you could have a sort of cable running through a concrete pipe, effectively, a tube of some sort. Would have a bearing plate at each sort of section of this sort of multi-stable core, potentially some compressible material between them, or potentially just a gap, depending on, of course, what you wanted. And you can see here that should there be tension on that internal cable there is going to be sort of high stress concentrations underneath the bearing plate. And the way in which you would design that is, of course, up for debate. It's not real. It's not a real project. It's not a real system that's been invented yet. So we can talk about what sort of things would be appropriate for that sort of structure. So if we go back to that list, sensor integration. Well, how do we integrate sort of sensors into such a detail? Well, we could talk about, for example, strain gauges, which would relay information back to a control system. We could talk about inclinometers, which would detect, how far over a certain section of the core is, whether it's uncomfortable for the residents or the people inside, the users of the building, and of course these actuation systems can actually reduce vibration through an active means. We're talking primarily about serviceability limit state here, not necessarily ultimate limit state. This is more for the comfort and reduction of any distress that the building occupants may face. Now, you may ask, well, what's sort of going on here with regards to this clutch mechanism? Well, I'll skip ahead and we'll talk about that in a moment. But from a safety perspective, this is something that we need to look at. In the case of a sort of power loss situation, we need to look at systems by which the building could remain safe, could remain sort of serviceable, for example, can be potentially repaired and such. And the idea is to potentially look at sort of, for example, bistable mechanisms, where a bistable mechanism has two stable states. So should such a mechanism fail due to power loss, similarly it will default into one of those stable states without power. And so we could look at potentially using a clutch mechanism for our cable, a clutch that is normally engaged, and so you would get load transfer through such a clutch, and then apply power, you would disengage said clutch and actually be able to tension the cables up. And so that's what I'm drawing in the gap just here between the two plates there. You've got a clutch plate and a bearing plate, and then of course you need a mechanism to then actuate the clutch, of course using power. So those are sorts of the sorts of details that we're talking about really. We're sort of looking at some of the sort of more speculative things and how we could potentially design them. And the idea is to sort of maybe feed that back into what we're doing today as construction professionals. Much science fiction has influenced things like mobile phones and telecommunications and technology, for example, AI. And I think it's a valuable resource in trying to sort of understand. Well, how does this all come together? Well, that's where sort of the computational core and the computational detailing come in for me. Traditionally, we look at analysis and design as a sort of pre-step to looking to build something or make something. And with the advent of things like digital twins, for example, we look at it from a maintenance perspective or from an asset management perspective. But fundamentally, sort of the analysis, the computational design aspect of it, especially with regards to finite element modeling and such, we look at sort of some of the analysis from the beginning of a project. Then that goes to either manufacturing or production, and then we get a product at the end, which generally for structural engineers tend to be buildings or bridges or something similar. But it could be a modular structure, it could be an infrastructure project, for example. But really, that's where this sort of the project life cycle ends, so to speak. But some of these details require something a little bit more. And so we get something more like this, for example, which is where the analysis model pushes into the actual product's design life itself. And so where we saw previously that the analysis was effectively just a roadmap to production, that is now becoming part of the data and part of the control system of the structure itself, along with other inputs from sensors, potentially environmental data, use data, and physical controls, potentially from a user. Then go into data. That goes then into an analysis model, a response model, and actuates the actual the structural or the building or the structure or the bridge or what have you. Right. So effectively, this sort of detailing of the future relies on sort of fundamentally, it relies on the computational model as a backbone, both in terms of design, but also in terms of control and sort of lifespan of the building. Effectively, the computational model of a structure becomes its lifetime analysis model. It becomes itself. The system relies on the integrated model's ability to adapt and respond to its environment right from the outset, right from the beginning of the actual design process. Effectively, the structure becomes part of its own digital twin, which is quite impressive. Like when you think about sort of the mind-body interface, and that's probably where the next slide is going. Yeah, that's right. The structure becomes part of its digital twin, and the structure is the body, and the sort of digital model becomes the mind. And with the sort of advent of artificial intelligence and various other things, you can sort of see a future where buildings effectively become their own persons or entities that have their own ability to move and adapt, and as we said, as we looked at previously, sort of the human body begins to react and live, to be pushed and pulled and various other things. So can buildings and structures generally. So thank you. That's all from me. Hope that was inspirational, and thank you very much. Take your questions now.
Thank you very much, Ashley. Now, Ashley is here with me as well. So I'm Rob. I'm co-hosting. Go. Thank you. We can see you, Ashley. Hopefully, we can hear you as well.
Hello.
Oh, excellent. Okay, everything is working. So, welcome, Ashley. Firstly, thank you very much for joining us on Innovate to Build and giving us an excellent session. Very informative and very information, as Carol has just put in the chat, so hopefully everyone can see the chat. We are here for the next 5 to 10 minutes or so, so if anyone does have any questions on Ashley's presentation, please feel free to type them into the live chat section of the interface.
I was just saying to Rob a few minutes ago that it's a little bit esoteric, so I can understand if you're a bit wary of speaking to me. So please don't be shy. It's incredibly speculative, I think. Although I think a lot of the times it is nice to sort of look to the future. Oh, Carol, hello. Do you have any suggestions for ebooks or content about this? There is a researcher at the EPFL in Switzerland or Geneva, I believe. His name is Gennaro Senatore, and he did some work on adaptive structures specifically. There is a sort of he did an expedition. He did an exhibition with a company called Expedition in London a few years ago, where the deflection of a cantilever was compensated for. I forget what it's called, but it was on at the building centre, and his name is Gennaro Senatore. So he's a good source for this. There is also another. It seems very sort of academic. There's also another researcher via the International Association of Shell and Spatial Structures. His name is Sergio Pellegrino, and he does a lot of deployable structures, primarily for space applications and orbital applications. He's a former structural engineer who's gone into aerospace, and he effectively designs foldable structures that deploy in space from a small package to a very large package, or very large arrays and such. So those are the two that I can think of at the moment. It's definitely becoming a little bit more mainstream. I use that word tentatively, but it's more mainstream than it once was anyway. So yeah, those are probably the two things really.
No, thank you, Ashley. And if anyone has any questions and you don't want to ask them in this open forum, it is possible to send us an email to marketing.uk@graitec.com, and then we can pass that on to Ashley and put you in contact with Ashley. And if you want to take these questions outside of this live chat.
No, that's no, I can understand it's a little bit it's more of an inspirational one anyway. So I'm quite happy to answer any questions if you send them through.
It's a great way for us in the UK and EMEA to finish the day with a bit of inspiration, and actually for Naima to wake up with a bit of inspiration as well. So it's a perfectly timed session.
Hopefully, wonderful. Thank you very much.
We'll keep the session running for a few more minutes, but okay, I can't see any more questions coming in. But please, while we have Ashley here and he's live in the room with us, please ask your questions. But yeah, we'll just leave it run for another minute or so, just in case anyone is still typing. Okay, so nothing more has come through. So once again, Ashley, thank you very much for presenting and being part of the Innovate to Build conference. To everyone who has attended, thank you very much for joining us. Final point, if anyone has missed any sessions from the conference, you can watch all of these on demand. Once the session is finished, you can watch it on demand again, and you can watch any sessions on demand from the conference. And that will run up until the end of the year, so plenty of time to catch up on all this great content. So once again, thank you, Ashley, and thank you everyone for joining.
All right, thank you very much.